Hi, everyone. I am Natalia, Director of Product at Cerebras Systems. At Cerebras, we are building a new class of computers designed from the ground up for deep learning. Cerebras is about large, actually very large processors and deep learning workloads which require massive compute resources, such as large language models. And large language models applied to long documents is large squared. So this is a perfect application for Cerebras. And today I'll share with you our work in progress on fine-tuning autoregressive large language models for long document abstractive summarization. What is summarization? You all probably know that. It's a task of generating a short summary from a long document. It is a challenging task, not yet fully mastered by language models. There are two main approaches to summarization with language models. The first one, the easier one, is extractive summarization, when the task is to select from the original document the most salient parts and phrases and glue them together to construct a summary. This approach is more likely to result in factually correct summaries, but often the resulting summary isn't cohesive and is not as concise as we want it to be. The second approach, abstractive summarization, is when summary or abstract is generated from text from scratch without copy-pasting phrases from the original document. This is often the preferred approach, but it is more challenging. It is more prone to hallucination and factual incorrectness, and it requires the model to be capable of generating grammatically correct text. For both of those approaches, most recent models used are based on transformers. So the most commonly used model for extractive summarization, or probably most well-known one, is the model called BERT-SUM. It actually takes a pre-trained BERT model and then fine-tunes that for a task for extractive summarization. You can see the architectural review of the diagram on the slide. So it starts from getting into the model representations of the input document. So input document is broken down into sentences. Every single sentence is tokenized, and you feed into the model token embeddings of those sentences, and every sentence is separated by CLS tokens and separator tokens. Then you also feed into the model so-called interval segment embedding, where you let the model know the borders between different sentences. So you will interleave segment embeddings within the long document, you choosing A or B embedding depending on the sentence. And then you also feed into the model position embedding. Then you have standard BERT model, and then you get out of the BERT model the representations, hidden representation of those CLS tokens. And then the task of the fine-tuning is essentially for every single CLS token to spit out a label. Should this sentence be in the summary or not? So for every sentence, you get a decision, should I copy-paste that sentence into my summary or not? That's how it works, pretty straightforward. Another approach, as I mentioned, is abstractive summarization, and many models which are used today for abstractive summarization are also based on transformers. One of the prominent one is called Pegasus. It's in the encoder-decoder model, as opposed to BERT being just encoder model. And it is capable to generate summary from scratch without copy-pasting or without marking which sentences should go into the summary. This model also uses a specially designed supervised objective called GCG, or gap sentence generation. This objective essentially masks the whole sentences from the document, and then the model is tasked to generate these gap sentences from the rest of the document. This pre-training objective works well for downstream summarization task. And at the end, when you use that model, you obviously don't have this objective, but your decoder part of the model will just generate the summary for you. What about lengths of the documents these models work with? What are some of the standard document lengths that can be used with these state-of-the-art summarization models? So BERT-SUM actually works with quite short documents. It is a fine-tuned BERT, and the original BERT has been trained with a context length of 512 tokens. So that means that it limits it to the documents of that length. Also, BERT uses trained positional embeddings, which makes it hard to expand the length of the document during fine-tuning. Pegasus use pre-trained model with the same context, also 512 tokens, and in fine-tuning they use a slightly longer context window of 1,000 tokens. But still, it's short for many summarization tasks out there. And in the paper, they actually point out that expanding to the longer context will be beneficial, but out of the scope of this work. Another prominent work on abstractive summarization is long T5 model, where the team took T5 model and trained it first on a longer documents of 4K 1000 tokens, and then fine-tuned for summarization with a much longer context. They used, to enable this fine-tuning on a longer context, they used sparse attention for fine-tuning. There is also interesting paper which provides an overview of long abstractive summarization and points some of the limitations of existing approaches. So they point out that most pre-trained transformers have an input length which is much shorter than what you want to use for summarization task. And they suggest to overcome that by kind of two methods. One, either fine-tuning with also sparse attention, or using an approach where you first shorten the document by choosing the cell length sentences, so similar to extractive summarization part, and then you apply abstractive summarization on extracted sentences from the document. So both of those are not ideal. So for the quality of models with sparse attention, the comment, although they are competitive with the state-of-the-art model, they are not better. And for approaches where you first reduce then summarize, it requires an extra step, and it's not always possible to do that. Let's look at also some summarization data sets and which sizes of the documents are present there. So this is a list of most commonly used summarization data sets available out there, and it shows you a number of training examples in number of documents in those data sets, and also average length of both document and summary. And we can see that for many of them, their average length of those documents is well beyond most common context for those models. So there is obviously a need to expand those models to longer context if we want to be able to summarize very long documents. But also, context size is not the only thing which we want to become bigger in these models. What about the model size? With the advances in large language models and with the existence of very large number of foundational models, it became clear that larger models are usually more capable in generating cohesive, grammatically correct text. So larger models are typically better. And actually, long T5 model is probably one of the largest models trained for summarization. They showed that increasing the model size helps with accuracy. So in this bubble diagram, the size of the circle shows you the size of the model. You see that long T5 is significantly larger than any other model that has been trained for summarization tasks so far, and it performs better than other counterparts trained even on the same context lengths. So larger model is obviously better, and we want those larger models also to go for longer contexts. But even the largest long T5 model is essentially just 3 billion parameters. Pegasus and BERT-SUM are in the range of hundreds of millions of parameters. At the same time, there is a rise of these large language foundational models, which are much, much larger. So today we have many of them open sourced, and we can actually leverage whatever has been already pre-trained on very long data sets. So on this slide, I show a number of probably most well-known foundational large language models. It took enormous amount of resources to pre-train them, and they have been pre-trained over a large textual data. So they know something about grammar, they know something about how to generate text, and it will be really good to be able to reuse those models for the summarization task. One downside, though, all of those foundation models are typically trained with the standard context length of 2000 tokens. So why is that? The next slide explains you why it's most probably the case. So on the slide, we show memory, which is required for training one of the smallest foundational model, GPT-J, as a function of sequence length you use for your training samples. And you can see that as you increase your sequence length from just a single token up to 2000 token, that's this data point right here, the memory requirement is almost flat. So that means it doesn't matter. It cost me the same in terms of memory to train the model on shorter sequences and go up to 2K. 4K right here is a little bit higher. So this is still tolerable, although already you see that there is a increase. Keep in mind that this scale is logarithmic, so it's significantly larger. And if you want to go to even longer context, you will need much, much more memory or some software tricks to be able to manage that memory requirement. So to me, that explains why most of the foundational models today are trained with the context of 2K. It's just this knee position on the curve. The plot will look exactly the same for other larger models as well. And also training with the kind of longer sequences is typically expensive. But what if we can train with longer context, with a kind of dense attention, and take advantage of ability of all the tokens to attend to the whole context? And also, what if we can leverage existing trained foundational models and essentially fine-tune them with a longer context? It's challenging to do so on GPUs today, but at Cerebras, we are lucky to have access to our hardware, to Cerebras Wafer-Scale cluster. In this work, we leverage Wafer-Scale clusters, which rely on the world's largest and fastest AI processor, our Wafer-Scale chip. It is packaged into CS2 physical system, which is also special designed for Wafer-Scale engine and for these deep learning workloads. And then we connect multiple CS2 systems together in the Wafer-Scale clusters, which allows us to get linear speedups from distributed training. All of that is used with the help of Cerebras software. This is also a very important component. It has been designed jointly with the hardware, and it's been designed recently. That means that it's been written while keeping in mind the latest requirements for deep learning, such as ability to easily run very large models without complicated distribution strategies, and also easily adjust those models to large inputs, such as long contexts. So no special code is needed for us to run those large models and to adopt them to run with longer contexts. Cerebras Wafer-Scale cluster, in addition to CS2 systems, has some additional components inside. So probably the most notable is MemoryX. That's our off-chip memory, which allows us very easily to deal with large models. So essentially, we can train multi-billion parameter models, all either on a single system or in a distributed cluster relying on very simple data parallel training. So with that, we can essentially easily take existing checkpoints in the range of 100 billion parameters and even beyond if we want to, load them into Wafer-Scale cluster with as many CS2 systems as we want, starting from a single CS2 system. Enjoy linear scaling to multiple CS2 with the easy data parallel distribution, and all of that using the code which has no model parallel complexity at all. So the code is written for a single node. And also very easy for us to deal with the larger inputs. So we don't need to think about things like gradient checkpointing and other approaches which are sometimes used to reveal that memory requirement I showed in one of the previous slides. So in a nutshell, essentially, we have access to the hardware and software, which makes it very easy for us to experiment with the large models and longer context. And that's what we've been done. So we've been lucky to be able to exploit how we can leverage existing foundational models and fine-tune them on longer context for summarization tasks. So we've started, as a starter, we took publicly available GPT-J checkpoint, which is 6 billion parameters and already above long T5 model. And that model has been trained on a context of 2,000 tokens, trained on a very large data set. So it's capable to generate cohesive text. And we would like to use that capability for the summarization task. So we've decided to take that model and continuously train that on summarization data sets with longer context and essentially see what happens. To start, we've chosen to work with the two data sets, which have examples of longer documents. So one of them is Booksum chapter, and the second one is arXiv. For both of those data sets, we pre-process the data, such as every training samples looks like first you have their initial documents. So in case of Booksum, it's a chapter, and then we have a special token and then summary. So the special token helps to prompt the model to generate summary. And the same is for arXiv. So then the original document is just article text, and then we have an abstract text as an example of summary. In order to experiment with this, we've decided that we would like to divide our training and evaluation data sets into buckets based on the sample length. So we bucketize that into samples up to 2,000 tokens, just to see how well we can fine-tune the model on this summarization data set to do summarization for those shorter documents. And then we have buckets of longer documents up to 4,000 tokens and up to 8,000 tokens. For the Booksum corpus, the precision with the shorter documents was very small, so we actually excluded that from the experiments and experimented only with the buckets of longer context. So what did we get from all of those experimentations? To get a sense how we are doing, we actually measured accuracy and perplexity on held out evaluation partitions of the summarization datasets. So on this plot, we show the relative performance of our fine-tuned models with respect to the baseline. Baseline here is the out-of-the-box GPT-J model, and we measure how well it can do on summarization datasets. So here, to dotted line shows accuracy and perplexity. Correspondingly, for BookSum dataset, it's orange, and for arXiv is this greenish color. So if you take GPT-J model out of the box without any fine-tuning at all, publicly available checkpoint, and you apply that for summarization task on the documents from those arXiv and BookSum corpus, you will get accuracy as shown here. So for BookSum, it's very low, it's around 20%, and for arXiv, it's a little bit higher. Suspicion is that because GPT-J has been originally trained on a pile dataset, which has arXiv as part of the training dataset. So that model is more familiar with arXiv text rather than BookSum text. So that's why we think, one of the reasons why we believe that it does better out of the box on arXiv data. And then essentially we took that GPT-J model and we continuously trained that on training samples from either BookSum or arXiv of particular lengths. So this data point here for arXiv shows the performance of the fine-tuned model on just shorter arXiv articles and abstracts. We can see it's a little bit higher than the out-of-the-box GPT-J, but just by a tiny bit, which is, I guess, expected. So we didn't extend the length of the context. We just tuned that model a little bit more on arXiv data, and hence we get a slightly higher performance. But then as you start to increase the context lengths for this fine-tuning data set, we see that the quality of the model goes up. So when we fine-tune the model on documents up to 4,000 tokens, we see significant boost in performance. And if we increase the context further, we see an additional boost in performance here. The same is true for the BookSum corpus. And these results are visible in both coarse accuracy and perplexity. So from here, we clearly see that exposing those models to longer documents makes a difference. So you can get your summaries of the higher quality later on. So this evaluation has been done on all evaluation samples. We didn't distinguish between shorter and longer articles in our evaluation data set. So that's just average performance of the model on all of the documents, no matter what context length is there. We also looked at bucketed results for arXiv dataset. So here we show how model perform on different subsets of the evaluation data. So here we partitioned our evaluation data set into different buckets too. And we measured scores separately for evaluation data sets consisting on only short documents up to 2,000 tokens, then evaluation documents with a length in the range between 2,000 and 4,000, and then also documents in the range between 4,000 and 8,000. And here I also show evaluation on all of the combined evaluation samples. So here we can see interesting results. So first of all, an interesting observation is that across all of those partitions, the best performing model is usually the one which has been trained on the data of the same length as our evaluation data set. So here we see then when we evaluate on 2,000 on the documents up to 2,000 tokens, the best performant model is the one which has been fine-tuned on the documents up to 2,000 tokens. And then their accuracy goes down for models which has been fine-tuned for longer documents. So that's probably also explainable in some sense that that model has been exposed just to that context length, and it tries to predict, like generate summaries from the documents, from shorter documents. The same is true when we look at the results on the 4,000 tokens and 8,000 tokens. So this bucket also shows you the accuracy of the model, which has been fine-tuned, like no fine-tuning at all, or baseline, fine-tuned on up to 2,000 tokens, fine-tuned on up to 4,000 tokens, and fine-tuned up to 8,000 tokens. There is a huge gap in performance when we go from models which hasn't been exposed at all to longer context to the models which have been exposed to longer context. But still, the best performing model is the one which has been trained on exactly the same context length as used in the evaluation data set. The difference here is not that large, but you can see that this bar is still higher. And the same can be observed on the evaluation precision with a longer document. So here we also see a huge bump from models which has been exposed only to shorter documents, the model which has been exposed to context of 4,000 tokens, and then another bump for the model which has been exposed to 8,000 tokens. So those bumps are expected. There is an interesting, I think, finding to be done why the models which have been exposed to longer context don't do as well on shorter context. One also of their theories that we have is that we probably need to train models for a little bit longer. So here on the right-hand side, I also show you the training loss curves for the fine-tuning models. So the red one corresponds to the model which has been fine-tuned on context up to 2,000 tokens, green up to 4,000, and blue up to 8,000. It starts again from the pre-trained GPT-J model, which has been trained with the context of 2K. And you can see that at the beginning, there is a little bit of jiggle for the model, which is exposed to exactly the same context, which is understandable. So the model has been trained on the documents of the same length, and we continue to train the model on the same size documents. So there is a little disturbance, and then the model starts to converge. For the models which are expanded and now kind of fine-tuned on a much longer document, this bump in loss at the beginning is much higher, and it's higher for longer discrepancy between context length which has been used for initial training and for context length which is used for fine-tuning. We can also see that those training losses continue steadily to go down. So we train that for a single epic for all of the documents inside arXiv dataset we have access to. And we see that there is definitely potential to go much down. So the loss curves haven't started to plateau yet. So this leads us to believe that if we expand the fine-tuning regime to longer and wait for the losses to plateau, we may actually even see the similar performance of models that has been exposed to longer context and shorter context when applied to shorter context here. So these are just very early results in terms of how those foundational models can be exploited for the task of summarization and how you can build from them models which can be used for summarization on longer documents. So in terms of conclusion, we believe that summarization task requires models which are capable to work with a long context, which are way beyond the standard context lengths that used for foundational models. Existing foundational large language models support shorter context than required. The recent GPT-4 model that has been released supports longer context, but it's behind the wall. So there is no way to take that model and to fine-tune that for your summarization task. All of the open source models that have been released deal with the context of 2,000 tokens. And the explanation for that is prohibitively expensive to train those huge models in much longer context. And we believe there is a way to actually still take advantage of those foundational models and continuously train them on longer context. So we see very promising initial results with this fine-tuning, and we will continue to work more and to experiment with additional models. For us, it's very easy to do this work because we can leverage the capabilities of the Cerebras Wafer-Scale cluster. So we can feed those models on a single device. We don't need to deal with a complicated model parallel training. Essentially, for us, we can easily experiment with the models in a large variety of sizes. We've started with the 6 billion parameter model, but we plan to experiment with larger models as well. And based on our other experiments with the fine-tuning, we expect to see better results with larger models. We also support long sequences out of the box. So for us, it's very straightforward to take a model that has been trained on a shorter context and then just bump a single parameter in the model and get it running with much, much longer context. Our initial experiments, we've been with a context of up to 8,000 tokens. On Cerebras today, we support context up to 50,000 tokens. So another next step in our work is also to increase the context size for our experiments. Another next step which we would like to exploit is explore foundational models with a different positional embedding. So GPT-J using ROPI positional embedding, which makes it somewhat easier to extrapolate longer context compared to trained embedding of a model like BERT. But based on the prior work, it's been shown that alibi positional encodings are even better positioned to this extrapolation. So in-house, we'll probably be training a model with a foundational model with alibi positional encodings and see how well it will be fine-tuned for summarization tasks for even longer context. I mentioned that we also want to do longer fine-tuning, so fine-tune potentially for longer than one epoch for the data sets which we have, and also explore find other larger summarization data sets. One other to-do item, obviously, these are very early experiments, and looking at the quality of the model using just standard language model metrics such as accuracy, perplexity, cross-entropy is fine. It gives you an ability to judge relative performance of those models. But in order to be able to compare with other summarization models, we need to evaluate those models using summarization-specific metrics such as Rouge. And that's another next step for us. So, as I mentioned, it's just the beginning of the work. We see very promising results where you can fine-tune those large foundational models for summarization tasks, and there is more to come. Thank you.